Good day, you fantastic human beings. In our previous class, we discussed the roadmap to various circle geometry questions, specifically grade 11 and grade 12 level. And in this video, we are going to use that roadmap and the diagram discussed in that video to discuss a circle geometry example. However, this one's an abstract proof, meaning we will need to discuss the value of one angle in terms of a different angle. All right, that's what the abstract proof there means. The roadmap discussed will be used in abstract proofs, solving for an angle, and then proving things like in this example where we need to prove something is a cyclic quadrilateral or something is a tangent line. Now, before we read through this introduction sentence, I just want to say, if you do not know what I'm speaking of when I mention a roadmap or a starting point for circle geometry, please pause this video and go and watch that video first to have an idea of where we need to start. Likewise, if you have not seen that video, but you know exactly what I mean, that is no problem. Please pause this video and redraw this diagram here because we need to go through our 9 circle theorems to identify different angles so that we can approach the 4 questions at hand, being proving that BODP is a cyclic quadrilateral, BF is parallel to PO, angle P2 over here is equals to a half angle O1, and FOP, so FOP, in other words, O1 and O2, is equals to 90 degrees plus angle B1. So it's quite a mouthful. If you could, please pause the video and go and redraw the diagram. Right, now, we need to read through what is given to us first before we can start our roadmap. They say here O is the center of the circle. Okay, there's point O. PB and PD are tangents to the circle at B and D respectively. So PD is a tangent and PB is a tangent at B and P. Just a slight informal disclaimer, this circle is not drawn to scale, my center is slightly off. All right, once you've drawn it, let's start with our roadmap before looking at the questions. Now the roadmap starts with the first grouping, which is the center of a circle. So I'm going to draw that quickly. Before, in the previous video, I used Roman numerals. Now we're looking at the center of the circle. And then I'm going to use a green marker to indicate the angles of theorems 1, 2, and 3. So we have a center point, which is given to us, fantastic. However, we cannot consider this point over here because it's not labeled. When points are not labeled, they generally will not appear in your memo. So you need to consider an alternative solution. So what we look at here is point O. Now, if we recall, we had a 90 degrees here from theorem 1, well, technically theorem 7, but we know theorem 7 is based on theorem 1. So we rushed a bit and we drew these two in. Then we went and looked at theorem 2, where we saw O1 over here was equals to 2 times D1. So it's going to put 2 arcs there. Likewise, angle O2 plus O3, I think we used the wiggly squiggly, was equals to 2 times angle F1 over here. So we did 2 wiggly squigglies. I believe we did 4 in the previous video, but for this one we'll do 2. Then we went and we saw, okay, is there an angle in a semicircle? Now we've got 90 degrees already illustrated, so let's use a highlighter to show this 90 degrees for angle in a semicircle. Fantastic. Now let's move on. For the second grouping, we look at cyclic quads, or like discussed in our roadmap, cocyclic points, which is theorems 4 all the way through to 6. Right. Now, we do not see 4 points on a circle here. However, they do say later we need to prove that PODB is a cyclic quad. So let's just keep a mental note of that quickly to see if we could talk about theorem 4 in terms of B and D, or B1 and 2 and D over here, or even angles O3 and B4, or P2 and D1. But we do not have that in a cyclic quad, so we're not going to note it at this point in time. Our next group was the tangent group, which is illustrated over here, which is theorem 7, 8, and 9. To those who have not seen the previous video, these are all Roman numbers that we just used to illustrate the theorem number, and it's just color-coded so that you can understand what is being drawn on the screen at this current time. Now, when we start with theorem 7, we know we've already done it, because theorem 7 and theorem 1 are interchangeable. I mean, theorem 7 is theorem 1 where the chord was pushed down out of the circle to only touch at one point. We've already illustrated that. Now we look at theorem 8, which says that 2 tangents drawn from the same point will have equal line segments, which means PB is equal in length to PD. And lastly, theorem 9, which I did mention was an all-time favorite, is seen over here, where we take the tangent where it meets this circle at this point. We look at the angle, so that's B1 and alternatively B4. But let's start with B1. We put both fingers here, take the one finger up to the F while the other one stays here. And you connect both fingers at the angle on the other circumference where they meet. That means B1 is equals to D1. So here, I'm just going to illustrate this for myself with a white double arc to show that B1 and D1 are equal. Likewise, B4 over here is equals, so let's do the wiggly squigglies, to F1. B4 and F1 are equal. Again, if you put both fingers here and you go where the angle is, so B4, your one finger is going up there while the other remains at B. And when you close your fingers, the angle it forms on the circumference is equals to the one that you measured here. So F1 and B4 would be equal. Fantastic. Likewise, over here, D2, if you had to go and form that circle, one finger stays here, the other closes here, and it goes up. So D2 is equals to F1. So let's do a white wiggly squiggly there. And if you notice, the double wiggly squiggly, sorry. If you notice, D2 is therefore equal to F1 and B4 because of the same thing. And likewise, we could have seen that D2 and B4 were equal because of the angles opposite equal sides with PD equal PB, which is our next point in our roadmap. Our roadmap's next introduction were triangles. We needed to look at radii, and this I'm going to illustrate with red ink. So I'm going to redraw my triangle in red here. Okay, where we start with triangles is we look at all the radii. All right, so we see OD would be equals to OF would be equals to OB because these three lines are all radii, which means, and I'm just going to draw a dot here, B2 is equals to F1. It's an isosceles triangle, so angles opposite equal sides. And likewise over there, let's use a little triangle here. D1 is equals to B3. Again, same reason. We see we have PB and PD, so we know these two are equal, but we have already illustrated them with the wiggly squigglies. And that's it for triangles. We also know we have an exterior angle of a triangle, which is equals to the opposite interior angles. And that we just need to keep a mental note of because there are quite a few of those here. Our last rule were line segments intersecting each other, where you have vertically opposite angles around the point and angles on a straight line. Keep that as a mental note because if we do any more writing on the sketch, we're going to get confused. But what you need to see is O1 plus O2 plus O3 is equals to 180. B1, 2, 3, 4 added together is 180. Vertically opposite angles here would have been these two and these two. But again, it's not labeled, so we need to ignore it. Well, not ignore it, but try and avoid it. If you are desperate, you can label it and use it. And then what else? Starting with the question, prove that BOPB, so let's just go over this, DP, sorry, is a cyclic quadrilateral. How do we prove anything is a cyclic quadrilateral? Well, we need to look at the groups of theorems that had cyclic quads in them. And that specifically was theorem 4, 5, and 6. So the second group in our roadmap. And what we need to realize, if we are looking at theorem 4, what we need to think of is proving that these opposite angles are supplementary, right? So to give you a better idea, using a highlighter over here, if we had to consider the cyclic quad in question, and I just want to point out there is an extended line here. If we could go and say, well, B1 plus B2 is equals to D1 plus D2, then it's a cyclic quad. Alternatively, if D1 plus D2 plus B3 plus B4 is equals to 180, then it's a cyclic quad. But to do this, let's take a look at what we had in our introduction. We saw that D1 and D2 is 90 degrees. And what was our reason? Well, that was the radius perpendicular to tangent, right? That was theorem 7. And likewise, B3 plus B4 is 90, or we could say B1 plus B2 is 90. Same reason, radius, perpendicular, tangent. Let's go with, for the sake of following the path of least resistance, let's go with this side. So B1 plus B2 is 90 degrees, radius, perpendicular, tangent. There we see there's a 90, then that's a 90. So exterior angle equals opposite interior angle. Therefore, BODP is a cyclic quad, and our reason would be exterior angle of quad equals opposite interior angle. Let's write that down. So we needed to start off by stating that D1 and D2 together are 90 degrees, and B1 plus B2 is equals to 90 degrees. So let's write that quickly. We could say here D1 plus D2. And another way of writing it would be ODP. So alternatively, O angle D to P is equals to 90 degrees. And our reason would be radius, perpendicular, tangent. All right, now good news, you don't have to write both of those. You only have to choose one. So you can write D1 plus D2, or you can write ODP. The notation is your choice. Now we need to go and write something about B. So we could say B1 plus B2 equals 90 degrees. And there's our same reason there. Radius is perpendicular to tangent. All right, and now for the proof. This is the converse of theorem 5 here. We can say, therefore, D1 plus D2 is equals to B1 plus B2. Okay, we don't have to give a reason there. We've both proven they are 90 degrees. We could just, for ease of mind, we could say equals 90 degrees. Sorry, just want to correct the symbol here. There we go, equals 90 degrees. And from there, we could say, therefore, and the question said BODP is a cyclic quad. And our reason would be exterior angle, so EXT angle equals interior opposite angle, or for the sake of English, opposite interior angle. For question 2, it's asking us to prove that BF is parallel to PO. Highlight that quickly as an indication for ourselves. And while I'm doing this, I'd like to point out, in your question paper, you will receive a diagram like the one I just highlighted on one of these duties in, or actual question, and it will be a smaller size. And then in the annexure, you should receive an enlarged version of this for you to draw on and scribble on and so on and so forth. My suggestion would be leave the smaller version alone, go to the annexure, so example, the bigger version, like what we used in the introduction. Scribble on that or with color and highlighters and things, but leave a blank version out for you to come back to and just look at the more specific information relevant to this specific question. Now, when proving lines are parallel, we need to consider the converse, con, of the fun statement. Okay, so in other words, if we can prove angles are corresponding, then we can prove the lines are parallel without actually using corresponding angles as a reason. Let me give you a silly example. We need to look at BF being parallel to PO. Spoiler alert, I'm going to solve this before pointing out to you. So B1 over here, we already stated was equals to D1, and that was the tan-chord theorem. And from the previous question now, we proved that I think it was BODP is a cyclic quad. So do you see angles in the same circle segment here with these two dots? I indicated them before starting this video. So what we see essentially is D1 is actually equals to P2 because we proved BODP is a cyclic quad. So D1 equals P2, angles in the same circle segment, and therefore we can say, well, because D1 is equals to P2, P2 is equals to D1, and because these two are equal, do you see the F forming? Let me just close the letter. There's an F shape, and if the armpits of the F are equal, then the lines have to be parallel. And that is how we are going to work with inverses or converses. My apologies. So where do we start with this? Well, let's quickly refer back to the introduction. We said in white over here, B1 equals D1. And we said, well, that's tan-chord theorem. And now after question 1, so new information from this part of it here, we've proven something's a cyclic quad, which means if you have to look at all the bow ties in question, we have angle P1, the triangle over here, equals B3. So if you just follow the bow tie over there, we also have D1 equals P2, we have D2 equals O2, and then O3 would also equal B4. But for the sake of this, what we wanted to see was B1 equals P2. You could have turned it around and proven that O3 was equals to F1, or you could have proven that B234 plus P2 equals 180 for Cohen's area. But again, we are mathematicians. We do not like too much work. We want to follow path of least resistance. And this question would probably have been 3 marks maximum. So we don't want to do too much work. We go for the easy stuff. Use what we wrote already. B1 equals D1, D1 equals B2. Therefore, lines are parallel. Let's write it down. So we need to start off in the beginning. What we summarized in introduction paragraph. And that was angle B1 was equals to angle D1 and tan chord theorem, THN. Fantastic. And then we could say, well, angle D1 is equals to angle P2, and that would have been angles in same segment, right? And then we could see, well, we've got a common denominator here. We've got D1 and D1. Well, therefore, those two are equal to each other. So we could simply write that. Therefore, angle B1 is equals to angle P2. And we don't need to make a reason because we've proven that there. And therefore, we can say, well, fantastic. Then, we repeat the question there. EF is parallel to PO. And our reason is corresponding angles are actually equal. Okay, and it's as simple as that. Let's push on to the next question. Question 3. So before we carry on, let's just quickly summarize here. We actually have parallel lines now, and we have a cyclic quad. We're not going to use them in this question, but it is important to keep track of what you have proven in case you need it. But this question is a typical example of an abstract proof because we need to classify something, so P2, in terms of something else, O1. And what we noticed when we proved this BODP was a cyclic quad, we don't have the center point. So we do not have theorem 2 here. But I want to revert your attention back to the beginning where we look at these green little arches here. We saw that O1 was double D1 using theorem 2. Remember, we focused on B and F. We went to the center, and then we went to the circumference. And just in the previous question, we said P2 and D1 are equal because they are angles in the same circle segment using the cyclic quad. So if that is equal to 2 times that, and that's equal to that, then that is, well, this is 2 times that, and that is half that. And without the word that, let's put variables to it. So O1 is equal to 2 times D1. D1 equals P2. Therefore, O1 is equal to 2 times P2. And if you had to just use inverse operations to get P2 alone, you could say P2 is equals to a half O1. So let's circle back. And for the sake of drawing it quickly, I just want to remind you, O1 is equals to 2 times D1. And D1 is equals to P2. So we're going to use that. Let us start at the beginning. So we'll write there, angle O1 equals 2 times angle D1. Reason, angle at center equals 2 times angle at circumference. All right, and then we could say, but D1 is equals to P2. That's already proven, but let's not be lazy. Angle in same segment. And after that, we could say, well, therefore, angle O1 is equals to 2 times angle P2. Don't need to give a reason for that. And to get P2 alone, we could say, well, therefore, P2. Now, using inverse operations, to get rid of that 2, we divide both sides. Is equals to 1 over 2 of angle O1. The final question is intriguing. So to start it, let's quickly review here. We have a cyclic quadrilateral. Fantastic. And from our summary in the beginning, when we started this and we followed our roadmap, we saw that B1 was equals to D1, and D1 was equals to B3. Just remember those are radii, so it was angles opposite equal sides, and B1 equals D1 was tan chord theorem. Now I want to remind you, because BODP is a cyclic quad, D1 is equals to P2. Therefore, to reverse, we can say that angle P2 is equals to B1 because via via. Okay, fantastic. Now, they actually asked us to focus on FOP, so FOP, which is O1 and O2, and they wanted us to classify that in terms of B1. Well, if I look inside this triangle ODP, can you see we have O3, we have D1, D2, and we have P. And if we remember from our summary, what was D1 and D2? You're 100% right. That was 90 degrees because radius perpendicular tangent. So if that's 90 degrees, now we've got O3 in terms of P1. And P1 and P3 are actually the same as well because angles in the same circle segment. So here we have very good news. We've got O3 in terms of P1. Now, if P1 is the same as B3 and B3 is the same as B1, then we have another statement very helpful to the course, is we have O3 in terms of P1, and then you can just replace P1 and B1 and get your answer. Let's take a look at what this would actually look like. Let's start at the beginning. So we could remind ourselves that angle D1 plus angle D2 equals 90 degrees, and our reason there was radius perpendicular to tangent. And then we could go and we could say, well, fantastic. O3 is equals to 180 degrees minus that 90 for D1 plus D2 minus angle P1, and our reason there would be the sum of angles in a triangle. And then just apostrophe S. Okay, fantastic. But we don't want O3. We want FOP, which is technically O1 plus O2. And that would equal 180 degrees minus angle O3. And then we've got sum of angles in a straight line. Now, what we need to do is we need to replace, we need to substitute O3 with what it actually is. So FOP would actually be 180 degrees minus, and just remember when you're replacing a variable, put whatever its value is in brackets. So minus 180 degrees minus 90 degrees minus angle P1. Now, if you had to simplify that, you would get positive 90 plus angle P1. Remember, you're distributing the minus in. For those that are slightly confused, this minus distributes in, and you would simplify and solve. Okay, fantastic. So we have FOP is 90 degrees plus P1. But what does the question ask us for? 90 degrees plus B1. And like I just explained, if we can show P1 is the same thing as B1, we're good. So let's go do that. So what we're going to do is we're going to start off with B1. We're going to say B1 is equals to D1, B1 equals to B3, B3 equals to P1, P1 equals to B1, and then replace. Let's go. Starting. Okay. Angle B1 equals angle D1. That was tan chord theorem. Then we can't just say angle D1 and D3 are the same. We first have to say OD equals OB, and that's radii. And now we can go ahead and say, okay, fantastic. If they are radii, then we have B3 equals D1. And our reason there would be angles opposite equal sides. And then to conclude here, we have, apologies, we have, well, B3 equals to angle P1, and that would be angle in same segment. And therefore, we can conclude now, P3 and P1 are the same thing. Therefore, P1 is equals to P1. And finally, if OP equals 90 degrees plus P1. I hope you enjoyed the video. Please remember to like and subscribe.